Hi, welcome to my channel, JaberTime. Here's another example. I just finished recording an example for first order linear differential equations. And here's the second example. I'm going to start by showing you the integral factor, where it comes from, and how it's applied. If you have watched the previous video and you want to skip to the example, I'll leave the timestamps in the description below so you could skip and jump into the example. So let's get into it. First order linear differential equations, they look like dy dx plus p of x, a function of x times y, equals another function of q of x. The function I of x, which is e to the power p of x dx, is called the integral factor. So in short, later on of writing all this, we just write I for the differential equation given to us, which is linear and it's first order. Since it enables us to reduce the differential equation to a form that is directly integrable. And this is how it works. If you take I, which is e to the power p of x dx times y, and we differentiate that, this is a product, so we're going to apply the product rule in derivatives. If this is u and this is v, the derivative of u times v is u times v prime plus u prime times v. So that's how we do it. We keep the first one, we differentiate the second one, and now we alternate and we do it the other way around. Derivative of y is y prime. Derivative of this right here, it's like another function e to the u. And to apply the derivative, it's the chain rule. Derivative of e to the x is e to the x, where derivative of e to the u is e to the u times u prime. And that's what I'm going to apply right here. That's e to the u times u prime. The derivative of u will be the derivative of this, which is an integral. That's going to cancel the integral and it's going to leave you with p of x. And I mentioned that y becomes y prime. But notice that we have this and this, kind of lengthy to say, but it's the integral factor, is in both terms. So we're going to pull it out as a common factor. Now I pulled it out as a common factor. From the first term we get y prime, from the second term we get p of x y. Now, what's inside parentheses is actually the left-hand side of the linear differential equation of first order, which is in short q of x. So we're going to replace that with q of x. That's the first order linear differential equation. That's how it's written. So we're going to replace that with q of x. Now, what does this mean? It means what we have here, after you find the derivative of this product, you get this, the following. Putting them together in one line, this is what I have. The derivative of the product rule of the product of these two functions gave me e to the integral of p of x dx times q of x. Now we need to reach out to y. So I'm going to integrate both sides to cancel d dx. With that, I'm going to get on the left e to the integral p of x dx multiplied by y, and the right hand side is going to show an integral, of course, with respect to x. In short, kind of lengthy to keep saying e to the power p of x dx, we're going to call it I. So this is going to be called I, this is going to be called I, and I times y equals the integral of I qx dx, where I is e to the power integral of p of x dx. And that's mainly the whole idea about this section. The only thing is just you need to practice and you need some skills of trig integration from calculus 2. This is my second example, but I'll keep adding more examples as we go. So first order linear differential equation, to summarize, looks like this. That's first order and it's linear. we are going to use I, which is e to the power integral of p of x dx. And finally, we're going to use I times y equals the integral of I times q of x dx. Or if you want to leave y by itself, y becomes 1 over I. Usually we leave that till the end. Then we divide by whatever I is. And that should do it. Here's my second example. We're going to start. 1 minus y multiplied by sine x dx minus cosine x dy equals 0. So it's not written in the way we like. We need dy dx. We need to see the first derivative. But if you want to see the first derivative, if you divide by d of x, you will see that, but cosine x will be in your way. So let's do it as two things, or two steps in one, or sometimes what we call it, two birds, one stone. So we're going to divide both sides, left and right, every single term also on the left, by cosine x to get rid of this, and by dx to get rid of this and show it under dy. So that's what we have. This cosine cancels. That becomes first derivative. That is 0. And that is actually 1 over cosine minus y sine x over cosine, because dx cancels. We're going to use the distributive property right here. We're going to divide 1 by, and we're going to divide y sine x by, and leave a minus sign in between. This is what I mean. Let's move this to the other side because we don't like the first derivative negative. We'll move this to the other side because to me it looks like y times p of x somehow. So this is y prime. Sine x over cosine x is tan x. 1 over cosine x is secant x. Moving this to the right, moving this to the right side, I get the following. So on the right side, I have y prime plus y tan x. Left side is just secant x by itself. Let's rearrange so we can compare it to the general form of the first order linear differential equation. Let's write this on the left and write this on the right. So now it looks like what we expect. Y prime plus p of x, that means p of x is tan x, times y equals q of x, which means q of x is secant x. Now, once we could identify that it's linear and first order linear differential equation, we could identify p of x and q of x. We go after I, and we'll take care of it. It's right here. I equals e to the power integral of p of x dx, and p of x is tan x. So that is my p of x. But tan x is sine x over cosine x. With that, we need to use u substitution. Let's call cosine x u. Derivative of u, which is derivative of cosine, would be minus sign. So if you write, instead of write du over dx, if you write du, that's going to be minus sine x dx. Let's leave dx alone. That's one way. So I could replace that and finish the u substitution in a clean way. So dx is the negative. We don't want to write negative in the denominator. du over sine x. Let's go back right here and replace dx and replace cosine x. So cosine x is u, and dx is replaced now. Sine x cancels. This simplifies to the following. Minus, let's put it outside, integral of du over u. That's known as ln u. This minus is in my way. We're going to take it back inside. That's log properties. By taking the minus inside, I could see that e and ln are directly next to each other, so they could cancel. And I end up with u to the power negative 1, which means inverse of u. I said to the power -1, but we meant the inverse. I mean the reciprocal. My mistake. So now we have 1 over u, and we agreed that u is cosine x, so that is 1 over cosine x, which is secant x. So this whole thing is I equals secant x. Now if you notice, if this is your first time to my videos, that I call my videos lecture notes with examples, because if I write this on the whiteboard as I go, it's gonna take a way longer than 14 minutes. So cleaning my notes, doing it this way saves a lot of time from recording and from you guys watching my videos. So I try my best to clean up my notes with colors, keep everything one side. As you could see, this whole thing is for I, we found it, and this whole thing is just to verify what is p of x and what is q of x. Okay, now after we find I, which is secant of x, we come back to the first order linear differential equation after we cleaned it up, so we could identify what's p of x and identify what's q of x. That's my p of x and that's my q of x, and that is a first order linear differential equation. We came with I equals secant of x, and after that we jump to the form I times y equals the integral of I q of x dx. That's basically a good summary of the problem, or the first order linear differential equation. So let's start right here and finish the problem. We have I times y equals, we know what's I, which is secant of x. Instead of writing secant of xy, I just pull the y up front. It's kind of cleaner this way, y times secant of x equals the integral. I is secant of x, but q is also secant of x. So we're going to end up with secant of x squared, or secant square x. We know how to integrate this because the derivative of tan is secant square. So that's going to give me tan. With the integral, because I don't have limits, I'm going to put the c, the constant of integration, replacing secant with 1 over cosine. Easier to get rid of and leave y alone. So I have 1 over cosine multiplied by y. Multiplying both sides by cosine after seeing tan as sine over cosine. Distributing the cosine to both terms. The cosine will cancel in the first term, and it's going to show next to c on the second term. So I do have y equals sine x by itself plus c multiplied by cosine x. And that should do it. Hopefully the notes are clear to follow. In short, that's what you need to know. You need to see the equation in the form that you could compare and find p of x and q of x. Go after I, find it, go back to this form and use it. With some trig integration skills, you should be able to finish the problem, and that should do it. Thank you. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.